In this video, we're going to talk about where to put the poles of our control system based on given specs. Those the specs in particular in this case are all in terms of the unit step response, and they are the rise time, 10 to 90% rise time, the settling time, and our peak overshoot. We've already talked about those performance measures. Now, if you are to meet those performance specifications, where should the poles of the system be? And we're going to base the pole placement on a prototype second order system. We'll talk about if your system is not really a prototype second order system, how to deal with those approximations. But as the first cut, we use the second order system as first cut of where we want the poles to be. Just to kind of review, we talked about this before, but the parameters of our transfer function, prototype second order transfer function, can either be in terms of damping ratio and natural frequency, or in terms of this sigma and damping frequency. And the sigma and damping frequency are the pole location. The pole is located at minus sigma plus j omega d. And it's also located at distance from the origin, that is omega sub n. Those are some geometrical relationships. I think we can relate damping ratio to it also, but I don't use that much. It's like an inverse cosine relationship. So let's look at things. You're given a settling time spec. We had this formula. Remember, we're using our formula sheet. I'll go back to the formula sheet yet again, way back here. This summary of formulas, we're using this. I'm not going to go back here over and over again. This should be copied and with a hard copy on your desk as you do any of this work. So settling time had this relationship. It's just 4 over sigma. And what is sigma? That's where it is in the left half plane. It's at minus sigma. So that gives us a line, this vertical line. And for settling time less than something, we need poles to be in the shaded region. If the spec says settling time must be less than something, that means the left of this line, where this sigma is calculated as 4 over the settling time. For the rise time, I won't go back to the formula sheet, I just promised, but we had two formulas for the rise time. And when we do this kind of thing, sketching where in the complex plane we want the poles, we use this simpler guy, which gives us what omega sub n needs to be. And omega n, remember geometrically, is the distance of the pole from the origin. So that gives us a number. It says we need to be so far away from the origin. The poles need to be outside this circle. And in fact, for a stable system, the poles always must be in the left half of the complex plane. We'll get to stability later, but we always want our poles in the left half plane. So that's what the rise time spec translates into outside this circle, to the left of that circle. What about the overshoot spec? Well, here's something from the formula sheet. Gives us a relationship between omega sub d, the damping frequency, and the sigma, which translates into these lines. All I need is the slope, omega d over sigma, right? So if you give me a sigma, pick any convenient sigma, ratio it up by this formula, and that gives me a point on the line. Now I just draw a straight line, and it's symmetric. Here's that other relationship with damping ratio that I never use. I use this formula, or this formula. You kind of forget about this. I just find it too complicated. What if you have all three together? You take the intersection. If I had all three specs combined, my allowable region is going to look something like this shaded region over here. That's the allowable region. That's the science of pole placement. You're just translating numbers using formulas. There's no fuzz on it. Where should you put the poles? That's where you get to the art of it. They have to be in the allowable region. But you just don't want to say, oh, let's put them way the heck out here and be done with it. There are reasons we'll get to later in the course you don't want them further out than you need. And a rule of thumb, meeting any spec, never exceed the spec by too much. They'll end up paying for it somehow, some other way. So stay kind of close to the boundary. Not exactly on the boundary, because we need a little room for error, but I call it stand in the corner. You're going to have some kind of corners probably to these contours. It's somewhere near them. And a little bit away from the real line if you can. We'll get into all these other reasons later. But here's about where I'd say you ought to put your poles if you had something close to a second order system. Now let's go through a few combinations. We went through them one at a time and then all three together. If you're given these two specs, just two specs, settling time and rise time. Well, those are kind of simple right off the formula sheet. Here's the formula for the sigma. It's 4 over the settling time. That gives us a number. That says this vertical line here, minus 1.5. The omega n, the rise time spec, gives us this circle. That's right off the formula sheet. The circle's 2.25. 2.25. If I want to find out exactly where this little corner is, I can calculate that. And I put the design points or the desired pole loop locations inside that corner. Stand in the corner, I say. So it's somewhere around here. That's the art of it. This should be shaded over here. They need to be somewhere to the left of this contour. What if I were given a settling time spec and a peak overshoot spec? Well, the settling time is easily calculated from the formula sheet. That gives me this vertical line here at minus 1.5. Peak overshoot spec gives me a relationship between omega d and the sigma. I already had the sigma, so in this case I calculated it exactly. It's at about 2 sigma, which is 3 here. So this corner is at minus 1.5 plus j 3. Allowable region, stand in the corner, I'll say it's about there, minus 2 plus or minus 3. Instead of right on the boundary. You don't want it right on the boundary, a little bit inside. But that's the art. Sketching this is a science. It's exact from the formula. What if I had a rise time spec and a peak overshoot spec? Well, the rise time spec gives me this omega sub n, which is this circle. In this case, 2.5. So there's that circle. The peak overshoot gives me a relationship between omega d and sigma. And to draw it, I could pick any convenient sigma, like 1. Then it would say, if I pick 1 for sigma, omega d would be 3.726, somewhere up here. just need a point, and then I draw a line through it. The origin. I have that line and that circle. The allowable region is to the left of that contour. If I want this point exactly, I do a little bit more algebra. And if I have all three, more calculations. Review. The settling time spec gives you a vertical line. Rise time spec gives you the circle. And the peak overshoot spec gives you this slope. This line. That's where to put your poles in the complex plane to meet certain performance specs.